Hello, everyone. Mr. B here, and we are currently in Chapter 3 of this class. And what it looked at yesterday was this whole idea of what a sensation is, which is essentially just our senses. And now we're going to look at each one in more detail, starting with vision. And we can't talk about vision without talking about light, because obviously that's what vision is. It is our eye's way of picking up on light waves. And when we look at all the light waves and wavelengths that are out there, there are far more that we can't see, what we can pick up on using things such as X-rays, microwaves, radio waves, etc., etc. But as you can see, on these wavelengths, where our vision is and what we can see is this area right here. Now with technology, we can see a little bit more. So now we have infrared technology, where we can look at infrared, but for the sake of this class, we're just looking at how our eye naturally allows us to see that teeny little part of the wavelengths. And so this is our eye. It is what we call our sensory organ for vision, because it's the organ that we use to help us see. And I'm not going to go into huge detail, but essentially what happens is light comes in through the cornea. And so the cornea is just that clear part that covers your eye. If you ever look kind of sideways at someone, you can kind of see that clear coating. It's far thicker on cats, so it's easier to see. It also helps to protect your eye, obviously. And then what happens is you have your iris, which adjusts reflexively to control the size of the pupil. And so the iris is kind of that colored part of your eye. So your iris can be different colors. A lot of that has to do with genetics and kind of where you grew up historically. And so all that the iris does is it adjusts. The easiest way to describe this is it's very similar to how the aperture on a camera works. And so if I quickly adjust it, you will probably see it getting bigger and smaller. All that this does is it allows less and more light to pass through. And that's exactly what your iris does. And so kind of that part that gets bigger and smaller, it's like the iris. That's essentially how the iris works. A camera is very similar to how an eyeball works, because obviously it's capturing images similar to how we see them. Alright, what happens next is the lens, which is kind of this, again, it's a clear part, but it's more on the inside of your eye, then focuses the light. And so this is the important part that takes the light waves in and then focuses on the back. Mainly the area known as the fovea, which is where your clearest vision is. And so it's essentially what you're directly looking at in front of your vision. Everything kind of around tends to be more fuzzy. But whatever you're focusing your vision on is then where that fovea is. And one more thing that I wanted to say, actually two more things, sorry. Then when this information has hit the back of your eye, there's all of these sensory receptors which we've talked about that then send it down the optic nerve. And the optic nerve is what then sends that information to the occipital lobe, which we talked about yesterday, is the part of your brain in charge of vision. But one other thing that I wanted to say is right where the optic nerve is the only area in the back of your eye that can't pick up on any light waves, because obviously that's where the optic nerve is. And so you have something known as a blind spot. And there is a separate video that you can watch today that helps you to find your blind spot. So I highly recommend trying the activity. It's only a 2-minute long video. It's a lot of fun. But when we look at the iris, again, it's that area that constricts and contracts. A lot of people don't realize that then the pupil, that kind of black dot in your eye, isn't a black dot, it's just a hole. And so this is a really detailed picture of what your eye looks like. And so as you can see, it's very fibrous, what your iris is. And then that constricts and contracts. And so the pupil is just a hole. It's just what the light comes in through. So I always found that interesting and figure I'd pass it on to you. And so this is kind of just a zoomed in version of the back of your eye. And so as you can see, there's all types of different cells. But for the sake of this class, the thing to remember is that the important sensory receptors are those rods and cones that then take in the light information, and they're essentially translating it to brainwaves. They're translating it into a message that your brain will then understand. That's all your sensory organ does. It takes outside information and translates it into a way that your brain understands. And then this talks about all of it, but you will not need to know that for the sake of this class. Now, when we talk about color vision and how we see color, there's actually two different theories as to what's happening. The first one is known as the trichromatic theory, and essentially what it believes is that there are three main primary colors to vision: green, kind of a blue-violet, and red. And the whole idea is the combination of these three colors then makes us see all the other colors out there. So it's really only three, and then the way that they combine help us to see all the other colors. And the way that we can kind of prove that this happens is the way that computer screens work, the way that projector screens work. Because if I show you this, this is a zoomed in picture of Wikipedia. And if you took a Wikipedia screen, whether it's on a projector, computer screen, TV, whatever, and you zoomed it way in, you would see these pixels. And as you can see, the pixels are only red, green, and blue, the primary colors. There are no other colors that are actually projected on a screen, and yet we see all of these different colors. There's another wonderful video that says this is not yellow, it's done by Vsauce, that helps to explain this in more detail. But essentially, this is proof that, we can see all these different variety of colors only with those three primary. Now, the other theory of color vision is known as the opponent process theory. That is kind of similar, but a little different. Again, it has this idea that there's three types of cells responsible for three types of kind of colors. And when they fire off, you see one thing, red, blue, and black. And then when they're not firing, when they decrease, you see the opposite. So instead of red, you see green. Instead of blue, you see yellow. And instead of black, you see white. And evidence that we have for this theory is something that is known as an after image, which I'm going to make myself disappear, and we are going to do very quickly right now. Now, what I want you to do is focus on the dot in the middle of the screen. Try not to look anywhere else. Try not to blink. Just focus very intently on the dot in the middle of the screen. I am about to change the screen, but I want you to still be focusing on that dot in the middle of the screen, trying your best not to blink for just a little bit more, a few more seconds, staring at that dot in the middle of the screen, not looking anywhere else, try not to blink. And there. Now, if you were staring at that screen, what you should be seeing right now, and you might need to blink or move your eye around a little bit, is a red, white, and blue flag. And essentially what happens with this is, I'm going to bring this back, when you were staring at this, these cells in your eye were firing over and over and over and over and over again for yellow, green, and black. And so when you were then taken to a neutral screen, those cells were so exhausted that they started to show the opposite because they essentially relaxed too much. And so that's the example of an after image. If it didn't happen for you, there's different examples. It depends on what you're looking at, if it's a really small screen versus a bigger screen. But that's just an example of how that theory of color vision also works. And then the very last thing is, of course, there are some individuals that cannot see all of these colors. For individuals that can only see black and white, they are known as a monochromat because they can only see one of the colors. Most people who can see all colors are known as a trichromat because they can see all three. But then there's a type of color blindness known as a dichromat, and this is when you can see only two out of the three. And so if you cannot see the shape that is in the right side of the screen, you might be a dichromat. And it means that you can only see two out of three of the colors. But that is essentially it for vision. Now we are going to kind of very quickly, because I don't want this video to be too long, but it is going to be a little longer because we are covering two senses in one video. But we're going to talk about now hearing and how hearing works. And so if we look at hearing, again, there's all these different parts of the ear. But if we break this down, you essentially have the outer ear, the middle ear, and the inner ear. Oops. And essentially what happens is the outer ear, just a tunnel. It's just the part of the ear that you see. All it's doing is it's bringing sound in. That's why if you go like this, you can actually hear better because it's increasing that tunnel. That's all that the outer ear does. In the middle ear, oops, this is where you have the ossicles. So this is the hammer, the anvil, and the stirrup. And essentially what it does is it takes in those sound waves, because that's all that hearing is. Again, it's waves, just sound waves that pulse through the air. And it takes it and it fine-tunes it to a point where it doesn't, make you go deaf. So it takes in that information and very finely tunes it. So then when it makes it to the inner ear, which has what's known as the cochlea, which is a type of shell, because it looks like a type of shell. There's all these teeny little hair cells, that line the inside of the cochlea. And so those sound waves, now that they're very fine-tuned, affect those hair cells, which we're about to talk about, that then, again, the hair cells are the important bit. They're the sensory receptors. They take those teeny little vibrations, and they translate it, again, into brain waves that then your brain understands, which again then goes to the temporal lobes of your brain. So again, all the sensory organs do is they're taking outside information like sound waves, light waves, they're translating it into a language your brain can understand. So then we can perceive our senses. And just a little bit of terminology when we talk about sound, we have amplitude, which is essentially just how high or low or how short or how tall a wavelength is, which affects how loud or soft something is. And then you have the frequency, which is how teeny or long one cycle of the wave is, and that affects the sound, in a sense, how it sounds, and pitch, essentially. And kind of just like vision, there's various theories as to how we perceive pitch. And essentially one explains how you hear lower pitches, one explains how you perceive higher pitches, and then one is how you perceive middle pitches. And so for the first one, for high pitches, we have the place theory. And the idea of this is that essentially, when these vibrations come in and are affecting the hair cells in your ear, it affects, and I'm actually going to bring it back, a different place in the cochlea. So there we go. So the vibrations come in, and if it's right here, you hear one sound. If it's further back, you hear another. If it's right at the beginning, you hear one thing. And if I recall correctly, it works kind of opposite of how you would think. So the higher pitch ones are right at the beginning, and the lower pitch, I believe, are towards the end. So that is the place theory. Then we have the frequency theory that doesn't so much matter where the vibration is, it's more how fast or how slow the hair cells are then vibrating. And this is used to explain lower frequencies, so kind of lower pitch. It doesn't matter so much where on the hair cells it's vibrating, it's more if it's vibrating really quickly or really slowly. And then we have the volley principle. And essentially, what the volley principle does is it takes a little information from place theory, a little information from frequency theory, and it helps to explain the middle ground. So I always think of kind of a volley going back and forth. It takes the information going back and forth to kind of fill in the gaps for, kind of that middle of the road hearing. Now, we can't talk about hearing without talking about hearing loss. And so when we talk about, again, the amplitude, the loudness of sound, we measure it in decibels. And the only thing that I want to kind of stress with this image is that a little bit over 80 decibels is when you start to experience hearing damage if you are exposed to it for a long amount of time. But the thing to note is that you don't experience discomfort from loud noises until around 110 decibels. And all that this means is that when you are listening to something super, super loud, even if it's not causing you discomfort, you could be causing permanent hearing loss. So turn that music down, take care of your ears, because once your hearing is gone, depending on the type, it doesn't come back. And speaking of the type, and I'm just going to make myself disappear because I can't move myself somewhere. There's two main types of deafness. You have conduction deafness, where it's damage to the middle ear. So again, it could be the eardrum, or it could be the hammer, anvil, or stirrup. And with this, hearing aids can help. So this is a way that you can kind of get some of your hearing back. Um, Nerve damage or nerve deafness, on the other hand, is damage to the hair cells. So again, this can happen from, being exposed to loud sounds for way too long. It happens naturally with the aging process. It can come from diseases. And a cochlear implant may help, which kind of acts as a natural, or sorry, not natural, an artificial cochlea, um, if only the hair cells are damaged. Um, but it cannot be helped or cured if it's the nerve damage, so it actually takes that information to the brain. And again, usually with cochlear implants, it's more for individuals that suffered from a disease earlier on in life, and so they get a cochlear implant, a fake cochlea. So again, just take care of your vision, or take care of your hearing. Also take care of your vision, very important. But that is it. I went a little longer than I was hoping. I try my best to keep it to 15. But we will be coming back tomorrow where we will talk about many, many other senses that we have, and some of them might surprise you.